Welcome to part 2 of the solar cell series. By the end of this video, we'll have everything needed for a functional extractor. We're in the middle of recovering 5 model parameters from the datasheet's 3 operating points. So far, by using a couple of approximations, we found closed-form solutions for the photo-generated current, the saturation current, and the ideality factor. But each of these expressions is written in terms of 2 parameters that are still unknowns, RS and RSH. There's not much information from the datasheet left to work with, and so we'll need to bring in a couple of conditions that arise from solar cell behavior. These conditions give us 2 more equations, and with no closed-form way to solve them, they're handled using numerical methods and solved simultaneously. There are different approaches for doing this, but in this case we'll do a 2-dimensional iterative solver using the Newton-Rhapson method. The equations fed into the solver will be set up as residuals, which are expressions that equal 0 when the target relationship is satisfied, and the solver adjusts RS and RSH until both residuals reach 0. The first condition we'll derive is the slope at the maximum power point. Previously, we've been looking at the current versus voltage curve, and the plot here instead shows the power versus voltage curve, with a clear peak at max power. By Fermat's theorem, the peak is a critical point, and the derivative of the curve at that point equals 0. So this condition is already in residual form. We just have to work out the derivative of power with respect to voltage and pin it to the max power point. Since power is the product of voltage and current, we can start the derivation there. And it's an application of the product rule, which gives us the expression I plus V times di over dV. Since VMP and IMP are 2 of the points that datasheets provide, we can plug them in to evaluate the derivative at that point. And we know the right side of the equation is 0. So the only unknown is di over dV. This one is an application of implicit differentiation. The starting point is the general solar cell equation that we talked about in the last video. One trick that you can do is instead of solving for di over dV, you can solve for dV over di instead. In my opinion, it's a little bit easier to solve for that one. After you have the answer, you can just take the reciprocal of it to get back to di over dV. We won't go through the full implicit differentiation step, but the starting point for it is shown if you want to go through it. It's just d over di applied to all the terms in the equation. The rest is relatively straightforward. You collect the terms, solve for dV over di, and factor into the form that you like. This is the form I ended up with. The photo-generated current term drops out since that one is a constant. As mentioned, we can take the reciprocal of the result to get back to di over dV and plug in the 2 datasheet points for max power, VMP and IMP, into the equation, since we're evaluating it at that point. So what we want to do next is get rid of the I0 term, which is easiest to do if we also replace the exponential term. Together, these 2 terms define the recombination current flowing through the diode at max power. In the last video, while deriving the ideality factor equation, we got an approximate form for this diode current term, so you can just replace I0 as well as the entire exponential term with what we derived there. You can manipulate it a little bit to get it into a slightly cleaner form, and this is the equation that will be used in Python directly. But right now what we have is the derivative of current with respect to voltage, and what we're really looking for is power with respect to voltage. That's the expression we got using the product rule just a bit earlier, but we didn't have the derivative term yet. Now that we have di over dV, we can plug it in, and that gives the full expression for dP over dV. The right side is 0 since we know that the slope is equal to 0 at the peak. And it comes out in amps, so the units in the expression do check out. This is our first residual, the maximum power slope condition. The second condition is a little bit trickier. It's the slope of the IV curve at short circuit. We can run through a quick derivation to pin down what the expression for that slope is. So let's start with the equivalent solar cell model at the short circuit point. If we apply KCL to this circuit, we get the expression where IPH equals the diode current plus the current through the shunt resistor plus the load current, which in this case is the short circuit current. Then, if a small change in voltage is applied to the output, say by changing the ideal short to a near ideal short, the currents through all of the branches change slightly. Photo-generated current is a constant, so that one does not change. Since the voltage across the diode is ISC times RS, it's very low, so the diode is pretty much off in this state, and the small dV at the output won't have any appreciable effect on the diode current. That lets us approximate the diode current term as 0. For the leakage branch, the applied voltage perturbation at the output will appear across RSH, so the change in current, according to Ohm's law, will be dVd over RSH. Let's define dVd. Since there's a small drop across RS, the diode voltage isn't exactly the same as the output voltage, So the change in voltage across the diode includes the effect of Rs. This means dVd is equal to the change in output voltage plus the change in output current times Rs. Substituting this definition into the small signal KCL expression gives the short circuit slope as -1 over the sum of RSH and Rs. But because Rs is expected to be so much smaller than RSH, we're going to go ahead and just neglect it. And so we'll say that the slope of this line at the short circuit point is -1 over RSH. This approximation actually matters in a subtle way. If we kept Rs, the residual built from this condition requires the change in diode current to be exactly 0 because that's what we assumed earlier. So it matches the approximation we made, but in reality, the diode current change is non-zero. It's just extremely small, and this inconsistency produces a residual that doesn't have a real root. So all I'm saying is that you have to remove Rs from the slope, otherwise this condition doesn't give us a residual that you can use. But as long as Rs is removed, we get a usable second condition for the solver, which is the approximate slope of the curve at the short circuit point. So here's the form that the quick derivation just led us to. But since we already have di over dv from the previous condition, from the maximum power point, let's take the reciprocal and move the negative sign over to the other side to isolate RSH. Once you plug it in, the negative sign even conveniently goes away. Last time we evaluated this at the max power point, but this time we're looking at the short circuit point, so that's what gets plugged in for I and V. So the voltage goes away because it's 0, and I becomes ISC. And then again, same as last time, we want to get rid of I0 from this equation, and we already have an expression that represents I0 from the first video. So it's plugged in, and after some rearrangement, we get this intermediate result. Since we want to use this expression as a residual, it should be in a form where it equals 0. To get there, subtract RSH from each part of the continued equality and then multiply each part by -1. That way the final result is the sum of dV over di at short circuit and RSH, and that result is equal to 0. So this is our second residual, the short circuit slope constraint. Together with the maximum power slope expression we got earlier, we have both equations for the solver and can set it up. Let's go through that next. The plot here is shown to try to visualize what the solver is doing. It's what we might see if we were to plot the IV curve at each step of the iterative solve. What it's doing is trying to pin down the curve to the points from the datasheet. For the solver, we're using the Newton-Rhapson method. A numerical method is necessary because the equations we have to work with can't be solved with normal algebraic manipulation. Here's a formula for one-dimensional Newton, and because the two-dimensional version takes a very similar approach, we can talk about the one-dimensional version first. Basically, in order to get an updated value of your unknown, you need its current value or an initial guess, and the result of the function you're working with x, the unknown, as the input. And you also need the derivative of that function. You can either solve for the derivative analytically and get the exact expression, or you can use a finite difference method. In this case, the derivative of both equations we have is difficult to compute, so we'll use the central difference method. In this method, you need to define a step size, which is h. And normally you just want the step size to be very small, but we're also going to scale it by the unknowns. This helps because Rs and RSH are very different orders of magnitude. So using the step sizes that are specific to each resistance keeps the step appropriate to its scale. It's also a good idea to put a floor function around h so it doesn't get too small. For two-dimensional Newton, linear algebra is used. We only need 2D here, but the method scales if you have more unknowns and equations. The 2D form is similar to one-dimensional Newton, but instead of dividing f of x by its derivative, the inverse Jacobian multiplies the f of x vector. X becomes a vector of Rs and RSH, and f of x is the vector of the two residuals we derived in this video. Again, these are the maximum power point condition and the slope of the curve at short circuit. I'll call these F2 and F3 as shorthand. We made sure that both of these are written in residual form, and the solver is going to adjust Rs and RSH until both residuals equal 0. The Jacobian is a matrix that contains the partial derivatives of each function with respect to each variable. It's the matrix of how each residual responds to each unknown. For a two unknown, two residual system, we end up with a 2x2 matrix. So let's go through computing the actual partial derivatives. After getting a scaled step size based on the current iteration's resistant values, we compute the partial derivatives using the central difference method. This is what that looks like for the derivative of f2 with respect to Rs. The f2 function is called twice, once with Rs plus the step, and then with Rs minus the step. Then you take those results and use them in the central difference formula. Since this is a partial derivative, RSH is held constant, and then this process gets repeated for the other three derivatives. This means to build the full Jacobian, we need to evaluate F2 at 4 perturbed points and do the same for F3. We also evaluate F2 and F3 at the unperturbed point in order to build the f of x vector. So that's the general idea for the partial derivatives, but there's one implementation detail that the simplified view we have here is hiding. And it's a part that usually trips people up. Every call to F2 or F3 requires n, the ideality factor, and n itself is also dependent on RS and RSH. So n has to be recomputed at every perturbed RS and RSH, or the Jacobian misses n's impact. It's cleanest to have a helper function take care of this for you, and that's the code block shown. The helper function is the compute residuals function. So at this point, we have the nominal vector f and all of the partial derivatives needed to build the Jacobian. The next phase is computing the actual Newton step. It's the inverse of the Jacobian multiplied by the f of x vector. At this point, you're doing arithmetic on the results of all the function calls in the previous step. Since this is only a two-variable system, the Newton step can be computed directly from the 2x2 Jacobian, and that's what I'm showing here. But for larger systems, you would usually use a dedicated linear solver instead of manually forming the inverse. And you can even do that for the 2x2 system if you want. Either way, once you've got the Newton step calculated, subtract it from the vector x to get the next iteration of RS and RSH. And this repeats until F2 and F3 results fall below the chosen tolerance. The chosen tolerance is a small number near 0, at a point where each iteration is barely changing the unknowns or the result of the residuals. I usually define it as a constant in Python, and you can do a little bit of trial and error to see what works best. Even with all of those calls to recompute the residuals and the ideality factor, the solver is fast and usually converges in just a few iterations. We're almost home, but we need one other solver tweak to ensure consistent convergence, which is to bound the Newton step. If we don't do this, an unbounded step can sometimes drive the unknowns to negative unphysical values, or create oscillation where the solver can't settle on a solution. So bounding the Newton step just means limiting how far RS and RSH are allowed to move in a single iteration. And similar to the finite difference step size, the limit can be set as a fraction of the current iteration's resistance value. This has the benefit of keeping RS and RSH positive, since each step is capped at a fraction of that resistance and can't push the updated value below 0. And it also protects the solve. Instead of jumping to an unphysical or numerically unstable point, the solver is forced to move gradually. Something like 5 to 50% of the value itself can be used as the step limit. For what we're doing here, 50% works out well. It converges, and it usually takes fewer iterations. But if you know that your initial guess is already close to the solution, a 5% step is safer. So that's basically the solver done, but we do need to have something for the very first RS and RSH that we put into the system. So what can be used for the initial values or estimates of the unknowns? Like one of the conditions used earlier, the tangent at the short circuit point gives us an estimate of RSH, and the tangent of the curve at the open circuit point is a decent estimate of RS. To keep it simple, instead of trying to figure out the slope of the tangent, we'll just use the slope of the line between the max power and open circuit points. That line is shown on the graph. The initial estimate for RS is then VOC minus VMP over IMP. For the RSH estimate, it's the same thing. The slope of the line between the short circuit and the max power points. The initial estimate for RSH is VMP over ISC minus IMP. This approach is very simple, but the initial guess for RS is overestimated, and the guess for RSH is significantly underestimated. So what you can do is multiply RS by 0.5 to adjust it, and multiply RSH by 4. Once these are scaled, you can use the formula we have for n from the first video. Compute n, and if it's smaller than 1, that means it's still unphysical, and we can keep going with this process. Multiply RS by 0.5, multiply RSH by 4, until you get to the point where n is greater than 1. This simple approach puts RS and RSH at a point where Newton iteration can take over and bring the solution home. And that's the whole extractor. Let's take a look at the Python code skeleton for it. To start, I use a factory method on the extractor class, and that's just so it can be extended later if we want to do slight variations of the extractor. For right now, it only has one route, which is the CellExtractor class. The functions in this class cover all the items we've talked about so far, computing the initial guess, running the Newton step, evaluating F2 and F3, and computing the photogenerated current and the saturation current. In code, the process ends up being that you pass the datasheet values into extractor.build, which instantiates the CellExtractor class. The CellExtractor runs the solve and creates a cell object containing the model parameters, and we'll talk about that next, including the forward model that lets you turn model parameters back into operating points on the curve. It might also be helpful to look at this whole process as a flowchart. At the start, we have the datasheet parameters and get initial values for RS and RSH. Then we run those through the initial guess loop, which scales the resistances until n becomes greater than 1. This moves the variables closer to the solution and helps with Newton convergence. Once n is greater than 1, we move into the 2D Newton loop, where our two-dimensional solver takes over. That loop runs until the residuals of F2 and F3 approach 0. The steps within that loop are all of the steps we've been talking about, computing the residual, checking whether they're close to 0, and if not, iterating and finding the next value of x, which includes applying bounds to the Newton step and getting a new updated x of k vector. Finally, once F2 and F3 reach a value that's close to 0, based on the tolerance we've chosen, IPH and I0 can be computed using functions we derived in the first video. At this point, we can take datasheet parameters and generate a full solar cell model. The extraction is complete. In the next video, we'll walk through how to get cell operating points from the extracted parameters. We'll go in depth on the application of Lambert W functions to this problem.